In this lecture, we are going to understand Kelvin double bridge. Now first we have to know what is the purpose of using Kelvin double bridge. Kelvin double bridge is commonly used for measuring low value of resistance. Now what is low value of resistance? In earlier lecture, I have already discussed that any resistance less than 1 ohm value is called low value resistance. So we have come to know about the purpose of using Kelvin double bridge. Next is why Wheatstone bridge that I have shown here in this diagram is not capable of measuring low value resistance. The answer is whenever we are measuring a very small value of resistance, then we have to connect it through this type of lead contact. These are called lead contact or lead connecting. So if we are measuring high value of resistance which are in kilo ohm or mega ohm, then this connecting leads doesn't have any impact on our readings. But when the value of your resistance value is less than 1 ohm, then this small lead contact's internal resistance has got a great impact on the reading. Why? Because if this lead contacts has got a very small amount of resistance, that is 0.5 ohm or even 0.05 ohm, then this actually increasing the value of your measurable resistance to 5% to 50%. See, this amount of small value of resistance is making so much difference in your reading, so that you will never able to calculate or measure the exact value of your element resistance. That's why this Kelvin double bridge is so much important in measuring low value of resistance. So we have understood first these 2 points. Now third point is why I have drawn here a Wheatstone bridge, or what similarity does these 2 bridges has common in order to measuring a resistance. We have to understand that Kelvin double bridge is a modification of Wheatstone bridge. Now your question will be how? So let us give the name of this particular point A, this particular node as B, and this is as C. This voltage source is connected to point A and C. Similarly, in Kelvin double bridge, this voltage source E is connected to point, suppose this point is A dash, this is B dash, and this is C dash. So E is connected with A dash and C dash. Are you finding any similarity? The similarity is, if I give this particular node name D, then this terminal, or I have shown it in blue color, is connected directly with this point, that is the D dash or this D in Wheatstone bridge. So what is the difference here? The difference is an additional resistance, this and this is connected with Kelvin double bridge. That's why it is called double bridge, because it has got another inner arm along with the Wheatstone bridge. So if I give the name this resistance of Wheatstone bridge P, this is Q, this is X, and this is S. Similarly, in Kelvin double bridge we can give it the name of P, Q, X and S. in Wheatstone double bridge, AC is here is variable. So that in Kelvin double bridge. So I think the similarity is quite clear, and we have learned another thing why it is called double bridge. Now same thing is here also as Wheatstone bridge, that is you have to first balance the bridge by making the galvanometer current equal to 0. Clear? Now next your question will be how these inner arms or inner resistances connected along with the outer resistances in Kelvin double bridge creating the difference. For that, let us give the name of this terminal as G and this is H. Whatever we found in Wheatstone bridge is X is equal to P by Q into S. This was the relation we obtained in Wheatstone bridge lecture. Now same concept is applicable in Kelvin double bridge, as we have to apply voltage division rule here also. So I am not calculating the entire derivation because this is a short course. When I will make a long course on this measurement series, then I will try to define you each and every derivation of all the things. Okay, so let us write the elementary equations of Kelvin double bridge. That is the voltage across this node, that is, or this branch better to say, that is we can write V A dash B dash is equal to voltage across V A dash G. Let us take this point as J. So V A dash G J, this is one of our equation. Next, V A dash G J is equal to V A dash G plus V G J. This is your another relation. So here we can write E is equal to, considering this entire path, E A dash G plus V G J plus V J H plus V H C dash. This is the expression of your E. So in this way we can formulate as our unknown resistance X is equal to, now this inner arm resistances, suppose this is small p and this is small q, and as I have showed, the connecting lead resistance that is creating the problem in measuring the low resistance is the resistance of this branch, that is GH, and this small resistance is denoted as small r. This is the resistance of the connecting lead that I have shown in the diagram earlier. So working on these equations, we can find X equal to P divided by Q into capital S plus QR divided by P plus small q plus small r into capital P by capital Q minus small p by small q. This is the relation that we find in dealing with these equations. Now here the very important thing that we have to understand, that our sole objective is to measure the value of X, not R, because this is the unknown resistance X and it is a very small value. We are varying S, we are connecting this P, Q as an additional inner arm in Kelvin double bridge to measure this X or unknown resistance, to cancel out this small contact resistance that is R. Clear? And the equation I have written here is the way how could we determine the value of this unknown resistance, that is X? Simply by cancelling out this whole part of the equation. If we cancel out the whole part, then our known resistance is P, Q and variable resistance S. We know already this. So how could we cancel it out? We can only cancel it out by creating the ratio of capital P by capital Q is very near to small p by small q value. This is the trick. See, if the ratio of this capital P by capital Q, that is the resistance of the outer arm, is suppose 3 and the small p and small q ratio is 2.9 or 3, then these two values subtracting each other are creating the value equal to 0. Anything multiplied by 0 is equal to itself 0. So we are getting simply from this equation X is equal to P by Q into S. That was our objective. This is the reason why the inner arms or the small p, small q, these were connected additionally with the Wheatstone bridge in order to make a Kelvin double bridge and calculating the small resistance value. Clear? Now let us understand the concept with an example. This is a Kelvin double bridge and the bridge is balanced. That means the current through this galvanometer is equal to 0. Clear? Now the outer ratio arms has the resistances of 100 ohm and 1000 ohm. So let us, this is P is equal to 100 ohm and the Q, this is Q equal to 1000 ohm, and the inner ratio arm, that is small p, is equal to 99.92 ohm and small q equal to 1000.6 ohm. This is given in the question. The resistance in the link is 0.1 ohm. Now what is the link resistance? As I have said earlier, this is the link resistance R, this branch. So link resistance is given here 0.1 ohm and the standard resistance, that is S, is equal to 0.00377 ohm. Now what is the value of this unknown resistance, that is X? So there is nothing complicated in this question. Just write the equation that we have obtained just now, that is X is equal to capital P by capital Q into S plus small q into small r divided by small p plus small q plus small r into, like this. So from here we can write this expression. From there we can write X is equal to 389 into 10 to the power minus 6 ohm or 389 micro ohm.